Today's lesson is 8.3 on geometric sequences and series. The definition of a geometric sequence is when your pattern is increasing by typically a multiple of a number, like when we're multiplying by times 2 between numbers, or maybe even a fraction, like times 1/2 or times 2/3. So there's definition a little differently worded is when the ratios of consecutive terms are the same. So a sequence A1, A2, A sub 3, A sub 4, A sub m is geometric when the number r is there such that A sub 2 over A sub 1 equals A sub 3 over A sub 2 and so on equals r. R cannot equal 0, right? We're not multiplying by 0 each time. And this time, instead of having a common difference, we'll have a common ratio because we're multiplying, right? We're not subtracting difference. It's common ratio for multiplying. So determine whether the sequence is geometric, and if it is, find a common ratio. So 5, 10, 20, 40, 80, right? Times 2, times 2, times 2. Looks good, yes? R is times 2. Next one, we got 3, 7, 9, 55, 63. Now, none of these look nice. Doesn't mean it wouldn't work, but I do 7 divided by 3, and then I'm going to test that against 19 divided by 7. 3 times 19 is 57. 7 times 7 is 49. Those do not match, so these fractions aren't equal, and so it is not geometric. Next one, some of these a little bit harder to see from the first two numbers. 486, 162, 54, 18. Oh, 54 divided by 3 is 18, or times 1/3. So 162 times 1/3, it looks like times 1/3 will work. So divided by 3, by the way, is a times 1/3, right? You circle the divide, flip it from being 3 over 1 to 1 over 3, right? And so yes, the ratio is 1/3. The formula for geometric sequence is a lot easier to calculate than the arithmetic one, and it's a sub n is the first term times r to the n minus 1, right? Because we don't calculate what would the first term be if we had already multiplied. We just do n minus 1 to cover that. So that way, when you plug in the first term, 1 minus 1 is 0, r to the 0 is 1, and we get the first term. So find the explicit formula of the geometric sequence and find the given term. So first term is going to be 3, right? That's given there. So we got negative 12, 48, negative 192, right? Our sign's flipping, so we're multiplying by a negative. 3 to 12 is times minus 4, times minus 4, and we get 48. Times minus 4 again, 192. So times minus 4 is the r. First term is 3, so 3 times negative 4 to the n minus 1. Just plugging it in, and then doing the calculation. 8 sub 12 equals 3 to the negative 4 times 12 minus 1, and we get this large number, which we can just move to this blank. But that is the answer, negative 12,582,912. Now, very large number, but because we're multiplying by 4, it doesn't take much to get to a large number. I mean, 4 to the third power, and you're already 64. Next one, 224, 112, 56. Looks like we're times half, right? Divided by 2 or times half. So 224 times 1/2 to the n minus 1. And now plugging in 12. So 224 times 1/2 to the 11 on the calculator, 0.109375. Technically, I would tell you usually to 3 decimals, but it went pretty long with that one. Sixth one, we've got the first term is 4, and the k plus 1 term is 3 times the previous term. So sounds like we're times 3, but like what I like to do is find the first 3 terms and make sure that pattern continues. So 3 times 4 is 12 would be the second term. And then 12 times 3 is 36. So my first 3 terms are 4, 12, 36, which it does continue the times 3 pattern. And so my sequence is 4 times 3 to the n minus 1. And now I'm going to plug in 10 for the n. 4 times 3 to the 9 gives us 78,732. Again, all these are calculated on your calculator. If you need help on how to do that, let me know and I can show you during a classroom session or Zoom. Next, we've got not so nice terms. Second term is 3. The fifth term is 3/64. Okay, so what's going on here? So we can't do the slope formula here because we're not increasing like a slope, right? This is technically How I like to think of it is if you draw blanks, we've got a sub 1 is a blank, and then the next blank 3, and then 2 more blanks for 3, 4, and then fifth term is 364. Now each term we're jumping by r. So what happens is we're going to do 3 over 64 divided by 3 equals how many jumps, right? From 5 to 2, 2 to 5, 5 minus 2 is 3, so that is 3 jumps. And again, this was kind of showing you how you can think about it as blanks, and we did times r, times r, times r. So 3 r's, r to the 5 minus 2, or r cubed, equals 3/64 over 3. And then when I simplify, times 1/3 top and bottom, we get 1 over 64. Those 3's cancel, we get r cubed equals 1 over 64, cube rooting both sides. Or you can do this on your calculator as 1 over 64 to the 1/3. That's another way to think about it. And we get 1/4 is our r. Okay? And then we've got a sub n equals a sub 1 times 1/4 to the n minus 1. Right? And we're going to plug in a sub 2 is 3. And so the opposite of times 1/4 is divide by 1/4, which would be times 4. Right? So we should get, if you're going backwards, we should get times 4 times 3 to get 12. But plugging it in, second term is 3, so this is 3, a sub 1 is still there, and now n is 2, so 3 equals a sub 1 times 1/4 to the 2 minus 1. This is a sub 1 times 1/4 equals 3, so multiplying by 4 on both sides here. 4/4 is 1, 4 times 3 is 12, and we get the first term is 12. And so now we've got 12, sorry, some of my boxes are still kind of being goofy. So 12 times 1/4 to the n minus 1, plugging in 7 to find the seventh term, and we get 3 over 1024. Typically, if you get a really messy decimal, and we've kind of dealt with fractions, you want to click the button that's going to make it into a fraction instead of leaving it as a decimal. Again, if you need help with that, I believe it is second. You hit the math button, and then the first thing on the math button says arrow fraction if you're on a TI 83 or 84. Next, sum of a finite geometric sequence. Whew, look at that formula right down there. This formula is what we're looking at right here. A sub 1 times 1 minus r to the n over 1 minus r. That is the sum of the first n terms of a geometric sequence. Now, these numbers can get very large. As you've already seen, the individual numbers like the 10th term, 7th term, 12th term get very large. These numbers will also get very large. Find the partial sum of the geometric sequence. We want the first 11 terms added together, and we got 2, 14, 98, 686. First term is 2. 2 times what is 14? I have n is 7. Sorry, r is 7. 7 times 14, 98, so we're good. So our formula is a sub n equals 2 times 7 to the n minus 1. And now, technically, you don't need to have that, right? Even though I mentioned it, we just need n, 11, first term 2, r, 7. That's all we need. I'm plugging it into the formula, right? Just a quick look. We need a sub 1, r, and n. So, again, unboxing these, we've got 2 times 1 minus 7 to the 11 over 1 minus 7. In the calculator, we get 659, 108, 914. Okay. Moving to the next one. We've got terms 1 through 15 of 10 times 2 to the n. Okay, so 2 is the base, but we need the first term. So plugging in 1, 10 times 2 to the 1 is 20. So there's our first term. 1 through 15 tells us n is 15, and now I'm ready to go. 20 times 1 minus 2 to the 15 over 1 minus 2. Gives us 655,340. A lot less work than the arithmetic one if you've seen that video, because it's just, we need less information and we usually don't have to do as much work to find that information. 10, we've got terms 2 to 10, so 10 minus 2 plus 1 is going to give us 9 terms. And we want to find the second term, right? Plug in 2. So 48 times negative half to the 2 minus 1, or to the 1, and negative half of 48 is minus 24. Plugging in, negative 24 times 1 minus, there is a negative half, the 9th power goes outside, all over 1 minus negative half gives us negative 513, 30 seconds. Next, we're going to do sum of infinite geometric sequences, and this will happen if r is greater than or equal to 1, we'll have no finite sum, right? I mean, if you're timesing by 2, you're always getting bigger. You're not going to approach a number as it goes to infinity. But as say it's a fraction, say if it's 1/2 or 1/3 or 1/6, right, or even like 5/6, we're going to approach a value eventually. It's going to get smaller and smaller and smaller, and we'll approach a value. So you would find that value by saying first term over 1 minus r. Basically, you want to say what's missing. We're missing 1 minus r to the n here. And again, why are we missing that? If we have a fraction here, this piece goes to this value specifically, r to the n goes to 0, right? 1/2 to the 100. Well, that's like 1 over some really, really big number. So 1 minus 1 divided by a really, really large number, pretty much 0. 1 minus 0 is 1, and we just get the top part. So that's why you basically remember one formula and remember what's missing for your infinite terms. Okay? So we've got from 0 to infinity of 4 times 1/2 to the n. Every time, take a peek, is 1/2 less than 1? Technically absolute value. But is 1/2 less than 1? Yes, then we'll have an answer. And then for first term, or 0 term in this case, plugging in, I get 4. 4 times 1, because this to the 0 is 1. And now I have 4 over 1 minus half. This part that's the base of the exponent is what the r is. And 4 divided by half is 8. Next time, we got negative 2/3. Is negative 2/3 less than 1? Check. Plugging it in. First term, 15 times negative 2/3 to the 1 is going to be negative 30 over 3, which is negative 10. Plugging it in, negative 10 over 1 minus 2/3. Yes, this becomes 5/3. And we get 1/6. Sorry, negative 6. Trouble reading here. And last one is negative 5/3 less than 1. No. So there's no finite sum. And then we'll get into some compound interest problems are on your homework. Just a reminder, that's what the formula is. A equals P times 1 plus R over N to the NT. I know that was covered quite a few chapters back, but just as a reminder for the homework that you are assigned. Next, finding the rational number representation of a repeating decimal. This is basically saying what fraction, right? Rationals, if you add the C and the F, becomes fractional, and that's literally what rational means. Any number that can be written P over Q, where P and Q are integers. So 0.36 repeating equals some number x, and then we want to move the decimal so that we get one series of the repeat. So in this case, two numbers repeat, times 10 times 100. So times 100, and we get 100x equals 36.36 repeating. And now, why we do it this way is because now when we subtract the top from the bottom, we'll be able to get rid of the repeating decimal. And when we do that, then we'll be able to solve for the fraction. So subtracting the 0.36 repeating and minus 1x, because 1x is 0.36 repeating, so subtracting, we get 36 is 99x. Divide by that, use the fraction button on your calculator, divide by 9, we get 4/11 is 0.36 repeating. Now this last one's one of my favorite ones because it's a little different than what you think. There are two ways to solve it. Typically I've done this right way, but I will show you it works both ways. 1.9 repeating equals x. In this case, I'm already giving it a negative sign because I know we'll need to subtract. So minus 1.9 repeating equals minus x. Times it by 10 because we only have one decimal here. Right? Last time we did 100 because there was two decimals. So we get 10x equals 19.9 repeating. And now 10x minus x, I get 9x. 19.9 minus 1.9 repeating, give us 18. Divide by 9, I get x is 2. So 1.999999999, etc. equals 2. It makes sense when you figure out what 0.1 repeating is. Right? 0.1 repeating is 1/9. So 0.9 repeating is 9 over 9, which is 1. Right? So a little tricky there. But the other way was to separate it and just say, well, we have 1. We're going to add whatever we get for this repeating decimal to 1. So 0.9 repeating is x. Again, 1 decimal, so times 10x equals 9.9 repeating, and subtracting the original, we get 9 equals 10 minus 1, or 9x, and x is 1. So 1 plus 1 is 2. And that wraps up today's lesson. Feel free to email if you have any questions on homework, lesson, or any topics.